I'm Johan. I'm Swedish, but I currently live and work in the UK. I've been a Go developer for 3.5 years. I'm a maintainer of various open source projects such as the grpc-gateway, grpc-go middleware, grpc-web, and TinyGo. I'm also a Go contributor, and I run my own blog, writing mostly about Go and gRPC. This is my first visit to St. Petersburg, and I'm here today to talk about TLS Certificate Distribution. Let's start with a quick overview. Today, we will learn about TLS and PKI, what it means for encryption and authentication, and a quick overview over how that works. We will look at how this is generally used today and problems with many of the current practices. We'll then dive into my new library, Certify, which simplifies and automates a lot of the tedious work in this area. We'll explore why and how it works under the hood. Finally, we should move one step closer to that fuzzy feeling of having successfully deployed mutual TLS for encryption and authentication. Why do we care about this? As application developers, whether you're writing mobile apps, backend systems, or command line tools, you have a responsibility to handle data safely. It used to be that only banks cared about using encryption, but nowadays it is standard practice for all engineers to know about and use encryption in their day-to-day work. Gone are the days of the demilitarized zone. Nowadays we have to design with security in mind on every level of the stack, and especially when transferring data between applications. This usually means using TLS for encrypting traffic, and we're going to look a little bit deeper at how this works today, and I hope to answer the question of how we can easily secure our data in transit. But first, let's look at some of the standards used. What is this TLS thing? TLS, or Transport Layer Security, is what underpins most of the secure traffic on the internet today. It is the next generation of the Secure Socket Layer, aka SSL, which was developed by Netscape for their browser back in the day. When SSL was adopted into the Internet Engineering Task Force, aka IETF, it was renamed TLS. We don't talk about SSL anymore, but if you hear it, some people use it synonymously with TLS, and they mean TLS. The latest version of TLS, version 1.3, was shipped in Go 1.12 and turned on by default in Go 1.13. It was standardized in late 2018 and provides many improvements over 1.2 in speed and security. TLS includes a record protocol, which is used to send data back and forth, and more interestingly, the handshake protocol, which allows participants to authenticate each other and negotiate encryption algorithms and cryptographic keys. Almost always, the standard used for this part of TLS is PKI. Well, what's PKI? Public Key Infrastructure, or PKI, is a way to map public key cryptography to identities, such as users or machines. It consists, at the most basic level, of a public and private key pair. The public key is what you show the world to authenticate yourself, and the private key is what you keep secret so that only you can identify yourself via the public key. But on the web, while a public and private key exchange would allow encrypted traffic, we also want to be sure that the server we are talking to is the correct one. That's where certificates come in. Certificates are a way for servers and clients to authenticate themselves via a so-called chain of trust. A certificate has a public and private key associated with it, and they are most commonly found in the X509 format, which we don't have to care about right now. The basic idea is you trust someone large and respected and trustful, a so-called certificate authority, and they guarantee that the website you are visiting is actually owned by the person or company that claims to own it. They do this by signing a certificate created by the website owner. So because you trust the certificate authority to carry out checks that the person creating the certificate is really the owner of the website, you can trust the website. In practice, you yourself don't have to trust a certificate authority because your operating system and/or browser will ship with some pre-trusted certificate authorities, and because you trust your browser vendor or operating system, you establish the chain of trust. The thing about certificates that complicates things further is that they have a lifetime, an expiry. After a certain time, they are no longer valid. So when working with certificates, we must consider how to renew the certificate. We'll touch on that a little bit later. So how does certificate signing work? When we say sign a certificate, what we mean is that we first generate a certificate signing request, aka CSR, CSR, which contains most of the information about the final certificate, such as the subject alternative names and IP subject alternative names. These names contain the domains and IP addresses we want to prove ownership of. The certificate authority takes the CSR and signs it using its private key, creating a certificate signed by the CA. As usual, it's very important for both parties to protect their private keys. So this is why you ideally don't ask for a new certificate straight from the certificate authority, since that would mean the certificate authority would have to generate a private key of the user before sending it to them. Using CSRs fixes this by allowing the client to generate its private key in place and just send the public details to the CA in the CSR. But let's take a quick look at the basics of a TLS handshake. We're going to look at the TLS 1.3 handshake, which is a little bit simpler than a 1.2 even. When you make a connection to a server, the first thing that happens is that the client sends some information about its supported ciphers and some random data. The server then replies with the chosen cipher suite according to what it supports and presents its certificate. If the client finds that the signer of the server certificate is someone that they trust, they can continue the handshake. And the client does this by looking into its certificate pool to see if any of the certificates in there is the certificate authority that signed the server certificate. And if it is, the certificate is trusted, and if not, the client can just terminate the connection. After this, if the server requested to see the client certificate, it's sent back along with the first request data, and the server gets a chance to verify the certificate of the client and terminate the connection. And if both sides are happy, the session can begin. So something that TLS 1.3 did there over TLS 1.2 was that the client sends the first request immediately with its first response. So it saves an entire round trip. All right, so how do we get a certificate for our servers? When it comes to acquiring a certificate for your website, you're faced with basically two options. You can self-sign the certificate, which is cheap, and you can make the lifetime of the certificate as long as you want. However, it's a little bit like signing your own homework. Why should anyone trust that you are the owner of a website when the person verifying that you own it is yourself? So you go to one of the large public certificate authorities, and you tell them that you'd like to purchase a certificate which expires in 1 year, and you have to prove that you own the domain you want to purchase for, etc. They then send you a certificate and a private key, and you have to manually make sure these files are accessible to your application, probably with something like a file amount. This is an expensive and manual task. Having to go through this every year for every application is against everything we're taught as programmers. There must be a better way. We must be able to automate this. Well, what if I told you that there was a better way? A new certificate authority called Let's Encrypt started with the idea that everyone should be able to encrypt their website traffic, not just large corporations, and that it should be free. Let's Encrypt has an API that issues certificates for free automatically. You've probably heard of CertBot, which uses Let's Encrypt under the hood. With CertBot, you just add a sidecar container to your application that automatically updates the certificate files on a mounted file system. All the steps from key generation to certificate issuing are completely automated. It does this by asking the requester to reply to a request in a specific manner and then makes a request to the domain the certificate is requested for. Because only the website owner would be able to make the server respond in such a way authenticity can be established. In Go, we have a library called AutoCert, which makes this even easier than CertBot itself. Anyone used AutoCert? You should check it out. It allows you to configure a callback that hooks right into the Go TLS stack itself. When a new connection is made, it can ask Let's Encrypt for a certificate right there and then. You can then cache the certificate so you don't have to request a new certificate on every request. This makes certificate management a complete breeze. Okay, great. We've solved all of our problems. Talk is over. Well, not quite. Let's Encrypt is great for running services on the public internet, where you can simply prove your ownership of a DNS record by replying to a request on your server. However, for internal traffic, which never touches the public internet, how could Let's Encrypt possibly verify that we have ownership of the domain we want to create a certificate for? What if we want to issue client-side certificates so that servers can authenticate clients too? Let's Encrypt also has a rate limit of 5 certificates per domain per week. And while this is completely sensible for a non-profit organization who handles thousands of requests per day, as a user, it can sometimes get annoying. What if there was something like Let's Encrypt that we can use for internal traffic? A certificate authority with a nice API that we can use to issue certificates that we can manage ourselves. Well, it turns out there are several alternatives in this space. At least 3 popular choices for rolling your own certificate authority. HashiCorp Vault is often used for secret storage, but also has a PKI backend. With HashiCorp's focus on security and cloud-native design, it's a great choice for your internal certificate authority, and we'll take a quick look at an example later. Another alternative is Cloudflare's CFSSL, which has more of an internal tool feeling to it than the polished Vault design. It's nonetheless popular and easy to use. A cloud-based offering is AWS's Certificate Manager Private Certificate Authority. AWS likes to call this ACMPCA, which is an acronym within an acronym. You are now subscribed to Amazon Acronym Facts. ACMPCA charges per certificate request, so it may be interesting if you want to do as little work as possible. There are other alternatives as well, but these were the major ones I could find. So how do we run our own CA? There are basically 3 steps to setting up your own certificate authority. First, you generate your self-signed, long-lived root certificate. You then take the root certificate and use it to sign an intermediate certificate. Finally, you distribute the root certificate to all of your clients and servers. We're now going to look at some brief pseudocode examples of doing this with Vault. To generate a root certificate, you can use OpenSSL or Go even. And here we're going to use Go. Give it a lifetime of something like 10 years, or sufficiently long that you're no longer responsible for renewing it when it expires. The private key generated with this certificate must be stored safely, ideally in one or a few physically isolated USB drives in literal vaults. This private key is very rarely needed and underpins the security of your entire CA deployment. So don't be like NordVPN, don't leak your master keys. Okay, so to generate and sign the intermediate certificate, we're going to use OpenSSL. This certificate should have a relatively long lifetime as well, something like 1 to 3 years, because you don't want to have to get your root certificate and key out too often to sign new intermediate certificates. An intermediate certificate is so called because it's part of the chain of trust, but it's not the root. It's any certificate in the chain that isn't the root, essentially. Once you have the intermediate certificate ready, you will need to install it in your CA. This differs between different options, but Vault makes this really easy by allowing you to generate the CSR for the new intermediate cert right via the API. We then sign this using the root certificate and key, and here we see an example of how to do this with OpenSSL. And OpenSSL is not making this particularly easy, requiring something as arcane as a config file to do this. And this part took me a while to get right, but it should work, so you're welcome if you want to copy that. Once you've signed the CSR with your root key and cert, store it back in Vault using this command. And then we distribute the root certificate. This sounds like a manual step, and you're not entirely wrong, but the good thing here is that you only need to redo this step if you regenerate the root certificate. Remember the one that has a long enough lifetime so as not to be our problem by the time it expires? That one. Fortunately, there's an easy way to do this on Linux systems. You're probably using Docker, so you'll just need to figure out where the CA trust store lives for your container base. It's going to be one of these, most likely the first one or the last one. Once you've identified which one it is, you just append your root certificate in PEM format to the end of the file. Make sure you do this as part of your container build so that it is applied after any operating system updates. And that's it. These files are automatically used by the Go TLS stack to create this default cert pool for applications. Note that this will keep your public roots in the cert pool as well, so if you want to be entirely sure only the certificates issued by your CA are used, either overwrite the file or manually specify the cert pool in code. And that's all we need to generate certificates on demand. Now that we have Vault set up with our intermediate certificate and we've distributed the root certificate to all clients and servers, we can go ahead and use Vault to both create certificates and sign CSRs. Remember what we said about having your CA create your certificate? It means it has to know and send the private key to the client. Much better than to generate a CSR and send that for signing. But some questions still remain. Now that we have an API to create certificates with, how can we trust that only those applications that should be able to create a certificate for a specific domain can? How can we enforce limits on certificate creation? As we briefly saw before, Vault has the concept of roles in PKI. A role can be assigned to a number of allowed domains, whether it should be allowed to use localhost, etc. This allows us to limit the domains that a client can create certificates for. Vault also has the concepts of policies and users, and it's possible to create a policy that only allows a user to use roles which match their username. So for our application, we will create a user called UW, after my employer, and the policy UW will automatically be mapped to that user. The credentials created are then distributed to the UW app, and it's able to connect to Vault, but only issue certificates for uw.com and uw.co.uk. This opens up some very exciting possibilities. So what can we do with authenticated certificates like this? Now that we've established that only the UW application is able to issue certificates for uw.com, it means that any services that uses the UW application as a client will be able to authenticate using the client certificate. It completely removes the need for machine JWT tokens for authenticating that the client is allowed to call the API. When we don't have to worry about machine authentication, it removes entire architectural constraints from our deployment. No longer do we need to issue and blacklist tokens. So how can we do this with Go? This is just something I put together quickly to show you how you can perform client authentication using the certificate. Visit my blog for an example of how to do this in gRPC, or just Google gRPC client authentication. It's the second result. The first thing you do is to ensure your server requires the client to present a certificate, which is at the top here, and that the server verifies it. This will guarantee that only clients with certificates issued by the trusted routes are even allowed to connect to your server. The second part here is a middleware implementation that wraps HTTP handler and checks that the subject common name of the client certificate is one of the permitted clients. This way we ensure only the UW app, for example, can connect to the server. Because only the UW app is allowed to issue certificates for UW and uw.co.uk. But wait, there's still a manual step involved here. We're so close, but we're not there yet. We have an authenticated API for issuing certificates, and we can limit which clients can issue which certificates. But the issuing step is still manual. But didn't AuthCert automate this part for Let's Encrypt? Can we do what AuthCert does for Let's Encrypt, but for internal certificate authorities? Can we automate this in the same way? Of course we can. I'm pleased to introduce Certify, a library which fills the same role for internal traffic as AuthCert does for public traffic. My wife came up with a name, and apparently it's very important that I mention this explicitly whenever I present it. It was inspired by AuthCert, but built specifically for use with internal PKI deployments. And it's as easy to use as AuthCert. You just configure it once and enjoy automatic issuing and renewal. Certify exposes a simple interface that can be used to implement your own issuers. It currently has built-in support for Vault, CFSSL, and AWS, but there's nothing stopping you from writing your own issuer and plugging it in. In addition to server-side certificate issuing, Certify also supports automatically issuing client-side certificates. It can do this because of the limitations we just discussed, where only certain clients are allowed to issue certificates for certain domains. There is no analog for this in Let's Encrypt or AuthCert. We'll see in a moment exactly how this works under the hood, but one consequence of this design is that Certify only requests certificates on the first request, incoming or outgoing, and you can manually make a request as you set it up if you need it cached immediately. I'm going to speed ahead a little bit because I'm running out of time, unfortunately. I wanted to mention that Certify comes with a sidecar container if you're not using Go. And this is an example of using the Vault issuer. As you can see, you just set the token, a role. You can configure how long you want the certificate to live. And you can specify things such as the other subject alternative names, which you probably don't need to set. And how do we use this with our service? You create a certify.certify type. You must specify the common name, must specify the issuer, and everything else is entirely optional. As you can see here, we've said that we want to issue certificates for uw.com, and we want the common name to be uw.co.uk. And then you just take the certify.getCertificate and getClientCertificate and assign it to your TLS config. And using the sidecar is as simple as just running Docker. I've created a Certify sidecar container that you can run. This is an example of using Vault, which is pretty analogous to the previous page. And as you can see, it just proxies traffic from 443 to localhost 80. It can't do client-side certificates yet because it can't capture outgoing traffic, but that's something that I would like to support at some point. If you have any ideas how to do that, then you're welcome to raise an issue. And then there was a little bit here about how it works under the hood, but I think we're almost running out of time, so I just want to mention briefly just the overview here. The green area here is the fast path. Most of the time, it will already have a certificate in the cache. It will not be due for renewal, so it just returns a certificate. In some cases, it will issue a call to an issuer and store the cert in the cache. The client side looks almost entirely the same, except if the server doesn't require the client to present a certificate, it won't even request a certificate. Otherwise, that is exactly the same. The Vault issuer uses the API, the CSR API, so everything is generated on the client, and it just sends the CSR for signing and returns it back again and to the API call. And to sum all of this up, let's take it one step further. We've automated everything from key generation to certificate issuing. We're using certificates for authentication. Our certificate issuing is now as easy as token issuing. Why are we even bothering with longer-lived certificates and the possibility of having to deal with revocation? What if we used token-scale lifetime for our certificates? Certify easily supports certificate lifetimes in the order of minutes. The only restriction is how often you can deal with the overhead of issuing a new certificate and how much load you want to place on your issuer. So summing it all up, we've learned about TLS and PKI. We know how certificates work. We know what a CSR is, and we know how a TLS handshake works. We've deployed HashiCorp Vault with PKI, configured it to discriminate between users to decide which user is allowed to issue certificates for a specific domain. We automated our internal certificate issuing with Certify, and we retired the tokens for internal service authentication in favor of validating the subject name of client's certificate. We're one step closer to that fuzzy feeling we discussed at the start. Thank you.
Thank you. Questions?
Hello, thanks for your talk. Can you say which advantages certificates have over tokens?
Cool, thank you. The question is, what advantage do certificates have over tokens? And the simple answer to that is that you're probably going, as long as you are already encrypting traffic, you're already using certificates. So it just removes an entire area of code from your code base. You basically don't have to worry about tokens. You're already using certificates. You may as well use certificates for authenticating the client, because that exchange of information is already happening. There's no extra overhead in using certificates. You just remove the overhead of using tokens altogether.
Any questions? Okay, thank you.
Thank you.